So also, thank you very much for inviting me. It's the second time I'm here, and it's actually great to be back here. Today I want to talk about semantic 3D reconstruction. So my work for many years has been on extracting three-dimensional geometric information from images. Many others have been focused more on extracting semantic information from images. What we've been doing the last few years is to focus on trying to do those two things together at the same time, and in particular try to do a joint inference of those properties. And so that's what I'll focus on in this talk. Before that, I'll give you a very quick highlight of a few projects we've been working on, and I'll be happy to talk to you about those offline if you're interested. So here's some work we've been doing on autonomous driving. In particular, so this was a project with Volkswagen and other partners, Bosch and many more, academic partners. Here are some of the parts that we worked on. So essentially the goal was to have an autonomous vehicle that would not need to have a laser scanner or other expensive equipment, but essentially close to market sensors. Relating it to Mobileye, this is actually meant to be cameras that actually look all around the vehicle, so you can drive fully autonomously in low-speed circumstances, so that you can essentially have your car go park itself in a parking garage. It's called V-charge. If it's an electric car, it could actually go charge itself, go back to a normal spot, etc. Okay. So what we do on the one hand is use the omnidirectional cameras for localization. Notice we're talking about indoor parking garages, things like that, so no GPS available. So we need to localize based on pure vision. So we build maps and then we calibrate. We do all these things are done fully autonomously. We recalibrate as the cameras are actually mounted on the rear view mirrors. This every time you have a slightly different calibration every time you start your car. Also, from the same fisheye imagery, we can very efficiently also extract motion stereo and get depth maps. And then from those depth maps, the video already stopped here. But from those depth maps, essentially also get full obstacle maps, at least of the static parts of the world, all done actually very efficiently on the equivalent of on GPUs, but also on essentially Tango tablet level. So NVIDIA K1, for example, does this in real time. And so we can get these type of maps. Of course, here also, as we heard earlier, it's very important if we could add semantics to this. Another project that we've worked on a lot is essentially applying all these type of technologies to drones, to small drones. Essentially make these fully autonomously, and as far as I know, we're the first to have fully autonomous, small vision-only drones that could operate essentially in cluttered environments, so no GPS or so, but essentially just flying based on vision, avoiding obstacles, and here the mission was essentially to fly autonomously and map out all the free space. Again, here we're limited by doing geometry only. We're very limited in what we can actually do in terms of missions. Planning free space is fine, so you can navigate, map out everything, but of course most tasks would require you to go beyond this. Maybe also something worth mentioning, my lab is actually also the home of the PixHawk project. For those of you working with drones, this is a project that does both software and hardware, open source hardware also. And for example, the PX4 autopilot was designed by students in the lab. So there's more information on the link. Then we've also worked a lot with Google on Project Tango. So here's again a few of the contributions. So in particular here, Project Tango is using an active depth sensor for indoor sensing of the environment. We've extended that to outdoor capability by leveraging the camera that's already in there anyways for motion tracking, and essentially use directly this fisheye image with the NVIDIA chip that's in there in this tablet to essentially calculate here depth maps from the environment. The nice thing is both that we can work outdoors without limitations of how much light there is, and also that there's no limitation on scale. If you move further, you can model mountains or you can model big buildings. And so we can here, by walking around the building, here some buildings in Zurich, you just walk around for 5 minutes and you have a model of the whole building. Of course, not everybody has a Tango tablet. Most people just have phones. So we've also worked in that space. And so what you see here is essentially a capability to make 3D selfies with cell phones, so for legacy devices, to be able to essentially build nice 3D models. We have a few startup efforts in this space. So one is a generic 3D capture on mobile phones, particularly legacy devices, existing phones that don't have 3D sensors yet. And also in particular, there's a startup effort on applying this in biometric authentication to really have true 3D verification of the identity. As you can see, this is all interactive real time on the devices. Okay, so now let me get to the main topic of this talk. So semantic 3D reconstruction. I'll present a few different things. So first, I'll talk about our joint reconstruction, recognition, and segmentation. In a sense, this is really doing what Jitendra has been advocating for a long time, to do the 3 R's, being in his words, reconstruction, recognition, and what was it, regrouping, or essentially segmentation. So to do those 3 things in one, or reorganization it is, to essentially do these 3 things in one, if you can do them together, because each of those subproblems informs the other subproblem. So if you have some information about geometry from the reconstruction, this can help you in classifying the scene. If you know where an object starts and finishes, this helps you with reconstruction, etc., etc. Then our initial model is a simplified one. Then we move to a full model that actually, what would be the right model to use, but this involves very high order ray potentials. For essentially every pixel we get a high order potential. This would be the correct modeling, but it introduces non-convexities. I will talk about that, and then I'll talk about a few more things if there's time. So the classical approach for 3D reconstruction, the pipeline goes as follows. This is something we're already doing. In '98, we had a pipeline. We were the first to have a pipeline that would do first structural motion, followed up by multi-view stereo matching. This was the Marc prize that was mentioned in '98. We're the first to essentially, from an image collection handheld, go to full 3D models with great, with a lot of details in the geometry. This is still essentially mostly the standard approach to do things if you do multi-view geometry. And the last step typically is to extract a surface, and that's typically done through a graph energy minimization. This graph can be a regular grid, it can be a tetrahedral or irregular grid, data-driven irregular grid. It can be both done with graph cut, or it can be done in a continuous domain. Essentially what you do is you separate space into the occupied part and the empty part. Can also be some real-time techniques, as in Kinect Fusion, but essentially you're optimizing something that looks like this ideally, which has on the one hand a term here where you put your data, and then on the other part a regularization term. And essentially most problems in vision get solved one way or the other in the end that way in the inference part. So in our case, the terms look as follows. We essentially, here this is 1 pixel, so we have a camera, we have 1 ray here, and we say in front of it here we put a penalizer, so we put something that will penalize this indicator function being 1, indicating occupied. So this will tend to make this 0, and then here we put a negative cost, which essentially means that here we get a bonus if we get this occupied here, and so we'll tend to occupy this part of the ray. Okay, so this essentially corresponds to our measurements, and if we put many measurements on top of each other, notice that as we deviate from here, the final surface, we'll have an L1 cost for this thing that is truncated at this distance, which corresponds to the uncertainty. Ideally, you'd like to say that all of this has to be empty, but that creates an asymmetry in this cost, meaning that then you pay a price in robustness. So there's somehow no ideal way to transform your essentially pixel information into a volumetric information. And I'll get back to that later. And then on the side of the regularizer, the standard thing to do is essentially say that you penalize surface area, and you do that equally in every direction if you don't have any semantic information about what you're looking at. But of course, if you're looking at these type of images, there's been great progress in classifying images, and essentially, and even people have been able to extract geometry just from this type of images. You look at this, it looks like a facade. The prior is immediately, this is probably a vertical structure. So Derek Hoyam work, for example, was able to create an approximate geometry just by looking at those images. Also, this looks like a ground surface. It's probably mostly a horizontal surface. We might not want to force it to be exactly horizontal, but at least we have a prior that most likely this is a horizontal surface. Okay? Or the normal to this surface is more likely to be pointing upwards. Okay? So what we want to do is essentially do jointly this reconstruction task, this geometric reconstruction task, at the same time as the class segmentation. Notice that the class segmentation essentially means that we do the recognition of labeling those different surfaces and actually delineating them, so doing the segmentation. All of this is now done. We want to do all of this at once. So in our formulation, we'll essentially end up with a multi-label volumetric segmentation problem to solve. Okay? So let me get very quickly in how we do that. So there exists a number of formulations to do multi-label segmentation. There's, of course, some GraphQL techniques. Here we'll talk about continuous solutions. Or essentially this can be solved by GraphQL, or it can be solved with a linear program by having continuous values at all those nodes. The advantage of this formulation, so this is a pretty old formulation, the advantage of this one is that it allows for arbitrary smoothness cost. However, the smoothness is only expressed directly across edges. It's not a continuous smoothness that allows for arbitrary normals. Boykov and others have proposed some methods to approximate better the smoothness cost, a more arbitrary smoothness cost, or more smoothness cost that would take normals into account, but better approximate the actual surface area, for example. But it's very limited in what you can do there, and it comes at a big cost of putting many extra nodes in your network. On the other hand, there's been continuous formulations, continuous in the domain, where, in particular by Kramers and collaborators, where in this case you have a continuous domain, you can do some anisotropic boundary length optimization in 2D boundary length, in 3D surfaces. But one issue is that actually the smoothness needs to reduce to a metric, meaning that if you transition from label 1 to label 2 and then from 2 to 3, this has to be cheaper, or it's always cheaper to transition directly from 1 to 3. Okay? And that's something that actually, for some of the things we do, is actually a disadvantage. So we've introduced a formulation that's inspired mostly from the continuous one, but is actually really expressed as a discrete one, so it's really somewhere mixed between the two. And we argue that we really get essentially the best of both worlds. Notice in the end, the continuous formulation of Kramers and colleagues, in the end, always needs to be discretized anyways. There's no way to work in a continuous domain if you actually do something on a computer. Okay? And so in our formulation, that's a modified version of that, and that you see the reference up there, we can actually allow for non-metric anisotropic cost between classes. And we can actually make those different. We have here we have a function here that expresses the regularizer that is actually indexed by the different classes, by the interaction between classes. So we can really express that. So let me show you here the formulation. So again, you recognize this unary term, the data term where we would put the data term on, and then the pairwise term that expresses the regularization. So this is a unary term. It essentially says if we like to have this occupied by this class or not, everywhere in the volume. And then, so this is where we typically put our data, our observations. And then, in terms of regularizer, we essentially now represent 3D normals in the space. Wherever we have a transition, we'll essentially explicitly have a transition happening with a certain normal direction. And we can now also penalize this according to this function, and we can define this function really depending on the specific classes that show up. Okay, so in terms of this anisotropic regularizer, how generic can this be? It turns out it can be very generic. There is some constraints, so in particular, so this is a concept that actually comes from crystallography. So these wolf shapes come from crystallography, and what you see here is the red curve and a black curve. The red curve corresponds to what a crystal shape you would obtain. For example, here, this would be the red curve would be the crystal shape. The black curve is the surface tension you need to apply. If you apply that surface tension for every possible normal here, then what you would get as a crystal is the red curve. Okay? You see that the black curve is non-convex. However, as long as the crystal shape that you get is a convex one, then the whole problem is still formulated as a fully convex problem. Okay, so we can do it's a relaxation, but it's in practice a pretty tight relaxation. As soon as there's a little bit of data, it goes mostly to fully binary solutions everywhere. We can essentially do anisotropic smoothness that's class dependent, and essentially put all of this in one big energy optimization. Okay? And we can relatively easily design these shapes or learn them from data. So I have data-driven smoothness priors that we learn from data. And at most, we need to do a convex approximation of these desired shapes, desired anisotropic regularization. Okay, so let's now translate this to our problem of doing 3D reconstruction, semantic 3D reconstruction. So we have a collection of images as input images. On the one hand, we use, you can use your favorite classifier. Nowadays, maybe CNNs, or it could be also random forest or other things if you want to have faster results. Here, calculate depth maps. Ideally, we do that also in a joint way, but I'll get back to that a little bit later. But for now, we essentially extract this separately. Here we, of course, have a full distribution. It's not just the best label. We can actually use a full distribution of probabilities here in case some of those pixels would be ambiguous in their classification. And here are our depth measurements. So what we want to do is bring all of this together in a joint fusion, which, as I said, we can formulate as a convex optimization into creating a dense semantic 3D model, where really now our volume is separated in a volume of building, a volume of vegetation, a volume of ground volume, and then a remaining class, and then for the rest it's free space as an explicit label. Okay, so we use this formulation. So we have our volumetric representation, and on the one hand, we put our data cost now, which was our previous geometric data cost, empty, occupied preference, and then here behind, we put a semantic preference. We essentially say, if we think the surface is here, then we say, well, here we're certainly behind the surface, inside the volume, and so if this looked like a vegetation pixel, then we put a small cost for instantiating vegetation and a bigger cost for putting another class that's less likely. Okay, and this way we can, in the volume, put a preference to rather switch on building or rather switch on the vegetation. And in this case, the vegetation is the cheaper option, so this is the one that will normally win out, at least if the rest of the data agrees with it. So that's on the unary term. Notice, of course, now we do this over all the classes. Only one class can be on, etc. And then we have this other term that essentially is now an anisotropic class-specific regularizer. Actually, not only class-specific, but it's really class-to-class. So we define, for example, smoothness for transition from free space to ground, free space to building. These are different types of anisotropic regularizers. This one, for example, is the one that we would learn. We actually learn also, at least for the classes we have data for, we learn this from data. This is an urban city model from Zurich that we received from the city of Zurich. And from this, we learn the statistics of the building, the orientation of the surface normals of buildings, and we also learn the ones from the terrain. Zurich is relatively hilly, so we have priors that we could actually have not perfectly, as you see up here. We don't strictly take, this would be corresponding to a vertical normal. There's a strong preference for that, but we can actually also have non-vertical normals. They are more penalized, but not prohibitive. So if the data indicates it should be a slanted surface, it will still get a slanted surface out. Okay, this is essentially all of the data that the different behaviors that we get. So we get building to vegetation stuff, and air always likes these vertical surfaces. makes vertical surfaces cheap to reconstruct and other surfaces more expensive, except when it interacts, as you see, with ground, and then ground is dominating. And then you essentially get building to ground is always has this horizontal preference. And so all of this we just put in our data, and then we essentially let the data and this anisotropic regularizer talk to each other in one big optimization. And this is what comes out. So this is the standard solution from geometry. In this reconstruction, we actually do exactly the same. We use exactly the same geometric data. Okay? So it's exactly the same geometric term. The only difference comes from this anisotropic regularizer, class-specific anisotropic regularizers. Okay? And so now if you look at this, what happens first is the ground diffuses out. And then look at what happens here. Okay? So you see here, this building initially was kind of floating around. You see it's actually mostly missing here. Why is it missing? Well, the person that took the pictures didn't take pictures from the bottom of that building somehow. And so that's missing in the data. So there we can't do anything about it. We have no priors. Here we know it's a building. Gradually the ground diffuses under it. And then as soon as it's under it, then it's pretty obvious. A building can connect straight to the ground. It likes straight surfaces, except that connection with ground, it likes horizontal surfaces. And it just comes out of this optimization with no effort whatsoever. And remember, all of this is a convex optimization. We just show the evolution here, but it always gets to the same minimum. We start from essentially from zero initialization everywhere. Also notice that in the beginning, the ground is pretty much the same as there. There's essentially no ground. So there's a few patches of ground. Why is that? Well, from multi-view stereo, a very oblique surface. And if you move around on the ground, you take pictures of facades, but not really of the ground. So the ground is very badly supported in the data. But if you have a small patch of ground, because of our anisotropic regularizer, it makes it very expensive to make ground surface that's upside down. So it's actually cheaper to diffuse the ground out than to wrap it up like this. And so gradually the ground diffuses out and goes here. And so with these very few interactions that you define at the voxel level, very local, essentially as in the molecules in crystallography, right? From there, it will gradually diffuse out and have really long-range impact on your reconstruction. With here even completing a building that's completely, so this, of course, is also not very fast because it means that it needs, the diffusion essentially is one step at a time, right? So one voxel talks to the next. So this is, of course, many hundreds or even thousands of iterations to actually obtain these results, to converge. But it's conceptually, of course, very nice to be able to do this. So here you see a zoom in on that reconstruction comparison, the semantic reconstruction and the classical reconstruction. So what do we have here? So essentially we get both a better reconstruction, a geometrically better reconstruction. We get essentially the missing data to be filled in as a person would do typically. At a simple level, but essentially you get a much more meaningful fill-in of your data with actually very little tweaks to the very little extra information you provided, just this anisotropic behavior. And also, of course, a much more meaningful reconstruction, because you now get a reconstruction that essentially, that has meaning. We know now this is building, this is vegetation, et cetera, et cetera. So here also, notice also that, of course, those surfaces now get separated. Here, we don't know what happens here, so it's connected because that's cheapest, it's less surface. We regularize for our surface amount. Okay? Here, well, these are different classes, so they cannot be just merged in one volume. They're always separated by a surface. And so this is a very nice property. You can actually see it here. So these are reconstruction, but actually, we don't need to do anything special to infer the surface of the building behind the tree. This is built in our method here. It cannot do anything else than complete the unobserved surface. Right? So we can split it out here. It has to complete the surface. It's not, this makes this method very, very different from a lot of techniques that also add semantics to 3D reconstructions, mostly by painting on top of the 3D model, painting classes on top of 3D models. This is a very different approach. It really does an inference of the 3D scene as a full volume, and therefore it has always closed surfaces per class, so the objects are closed. We really have the ground surface below the building. Behind the tree, there's always a building surface inferred, and it gets inferred, of course, as a minimal surface according to the known to the anisotropic regularizer that's specific to the interaction between a tree and a building, right? So here's a few more examples. So as I had indicated, there was still one real issue with this modeling, which is that we translated information that we get from a pixel, which is both a class information from the classifier as well as geometric information of the expected depth or even depth distribution, if there are some ambiguities or we have missing data, etc. We translated that all in the volume, completely forgetting where the information was coming from and the relation of visibility along the ray, which is critical. In vision, everybody knows one of the most critical things about interpreting 3D scenes is the visibility, is properly treating visibility. So in other words, if I look here, so for example, if I look down there, I don't see your feet there, for example, because I see this vegetation in front. This type of behavior, meaning that if I stand here, I do see it, this type of visibility relations is completely missing so meaning that if I thought that was the depth, but then actually this was the depth, and somehow things change, I will not be able to reinterpret my data if I put it all in the volume and forget about where it came from. So what you really want to do is to express it as a high-order potential that relates all of the voxels along a pixel ray. Now, of course, this is expensive, and it's even questionable if this is even doable. We had a first approach where we went back to graph cut techniques and discrete representations at CVPR 15. The approach worked, but didn't work so well and had many issues, and we had to forget about the anisotropic regularizers. Now, as a preview of CVPR 16, we can actually do it all back in the continuous domain, but we have to introduce a non-convexity, and I'll get to that in a second. Essentially, our high-order potential for a ray becomes essentially a potential that says along the viewing ray has both a depth label, a depth and a label, a class label, and essentially in the most generic form, we would have a potential that looks like this, which has, depending on which depth we select and which label, we have a certain cost to this hypothesis. Okay? And really, it's not only this, but we're really talking about this label is really assigned to the color or the label essentially of the first voxel that's occupied. It also means that everything in front of it should be empty. So it's really whatever happens is the first voxel that is occupied, that's the one that we pay the price for. Okay? And we want to optimize everything globally so that everything is empty. The first voxel that happens to be occupied, that's the price we pay for the depth and the label as a joint, based on that jointly. And anything behind it, we don't care at all. And that's the beauty about visibility, is actually that there's only one thing that's visible, at least if we don't assume there's no transparency and other effects at this point. Essentially, the first thing we see, that's what matters, and everything behind it is occluded. And that's actually also the only reason why this is still somewhat tractable as a problem, because if you had to do a high-order potential that links n voxels, with each of them being C different classes, then you have C to the power n possibilities, which would be completely untreatable. But in this case, the states that you have to consider are actually linear in the size of your ray, because you have n pixels. All of them have to be empty up to the first pixel, and then that one have one of C classes. Okay? So you essentially have n times C possibilities here, and that's it. So that actually means that it's possible it's still a tractable problem thanks to that property of visibility. Okay? So here's then how the formulation ends up being, at least in a sketch. We end up with this non-convex term here. So we have to take into account a non-convexity. We see that in practice, with reasonable data terms, this still converges very nicely and works very nicely. Okay? But we can't prove anything as it's non-convex. But essentially here, we get a switch. So if we know that we're in this situation or in this situation, then the problem is convex. But the fact that we have to switch here, that there's a max, that actually, this is the non-convexity. So our representation is as follows. On the one hand, we still have our volume representation that is global. That's the same as before. But now we also have, for each view, so for all the pixels in each view, we essentially have a local volumetric representation, okay? Which has to be, essentially has labels that this is free space, up to the first voxel. The first voxel gets labeled as a particular label, and then if anything behind it is strictly 0. Okay? And so these constraints here, this and the other constraints above it, enforce that, that this is the case consistently. Okay? In particular, this thing here is really switching between two modes. This part is essentially when you're here, and you have the previous voxel, this one, -1, previous voxel empty, and then from that you subtract that the next voxel is occupied. Okay? That essentially means is occupied in here. Then this is actually this situation where you have the first voxel becoming visible. After that, you have to switch to this mode, and this is also enforced by these inequalities here that says that that is always strictly, what is it? This is strictly smaller than this here. So whatever labels you put here, they're strictly smaller than these ones, for the occupied at least. And the key thing is that essentially here, whenever you raise the air, so the first thing you see, it has to move up with the same occupancy here. That's what this mode is. But then as soon as you've reached the maximum and you go back down, this one doesn't follow. It immediately goes back down, but then it never goes up again. So at the next the hard thing is actually you have one transition, great. So you see voxel. But then in the volume, a little bit later, further in the volume, you get another transition up because there's like a second surface, right? So it's like here, I see a first surface, behind it there's a second surface. Here, you will have a second surface appearing somewhere. The key thing is to not have that reflected in here and not pay the cost for that. Okay, if we pay the cost for that, then it's easy, it's all convex and it's all simple, but it's the wrong thing to do. So this is why it gets all complex there, or non-convex, is essentially this to model the visibility correctly. Okay? Essentially what we do in the end is really, we try to solve this inference problem from all the data, get this model. This visibility, as I modeled it before, really means that the model we get directly essentially generates depth maps and generates label images, and we pay exactly the price for the difference between this and this here, right? Up to the convex, the non-convexity, and the relaxation. Okay. So that's the key thing here. What's actually really surprising, so this both improves, of course, our results on the multi-label cases, but actually we went back and used this visibility modeling. We used this also on standard. There's not many benchmarks actually on semantic 3D, so we actually moved back to the classical benchmarks on just two label problems. And it turns out that, at least for some of the things, we actually significantly outperform, to our surprise actually, on some of the data sets, significantly outperform the state of the art. So actually, if you look at this column here, so we're not everywhere the best, but if you look at this one, it's actually quite surprising that a completely saturated benchmark, that's not more saturated than this multi-view, simple multi-view objects. People have engineered this to death. And essentially, in particular, Yasu Furukawa has really spent a lot of time on getting the best possible result. And suddenly we jump here by, if you look at the saturation point here, and then we jump by a significant amount, just by using essentially this proper visibility modeling, which was quite a surprise to us. And of course, something that's less a surprise to us is that a big problem in all this volumetric fusion, when you forget where the data comes from, is if you have two opposite surfaces. So you have a thin surface. Because saying that it's empty before and occupied behind, and then you do the contrary from the other side, this kind of fades out all this data. It's counterproductive if you have it from both sides, and you tend to essentially lose. Also, it's a lot of surface area for very little profit. So typically, you tend to completely lose these thin surfaces in this type of fusion approaches. Now, in our case, well, from both sides, we say that we want something occupied there, and we don't care about what happens behind. So in our case, it actually will very naturally just reconstruct nicely this thin surface without anything special to do. So it's a nice feature here of the method also to handle that. Of course, we'll do the same in the multi-class case also. Okay, so then very briefly, I'll talk about the other topics. So as I said, it actually makes a lot of sense to look at depth and classification at the same time. So we did some work in 2014 with Jambo Shi and Lou Morladisky in my group. Jambo was visiting at the time. Essentially, this is the standard classifier we used then, and then here, the joint classifier for depth and class actually outperforms the learned classifier on class only, surprisingly, although we solved this other problem also of recovering a depth. Or actually not so surprising. So essentially, the key idea is that if you learn, with whatever learning algorithm you use, if you learn class, if you learn appearance of a class, one of the main effects, one of the main noise effects is essentially that you see things in images at many different scales. And if you think of what we do at the low level on images, well, we're really, in a signal processing sense, we're really doing even CNNs and so on. They're just doing correlations with little templates, with little filters, which all have a scale, as we know. They all have a particular scale. So if we need to learn stuff at different scales, texture at different scales, what are we doing? Well, we'll essentially be learning in parallel, spending a lot of the capacity of our learning algorithm on learning things at this scale, and then separately learning that different filters, different frequency patterns shows up at a different scale, and so on and so on. So we need to learn exhaustively all the visual scales. So this was actually implicitly, avoided in object detection, because if you detect objects, then you actually do sliding windows, or you do whatever, and you essentially go over the window, and you do this at different resolutions. But for scene understanding, where you essentially try to classify the scene, people didn't do that explicitly. But you should also do it there. In hindsight, it's a very trivial observation. But essentially, if you learn cars, these are actually still objects, but vegetation or buildings, these things don't have a real scale, so you can put a bounding box around them. But still there, you should still learn how things look at one particular scale, and then handle the different scales actually through a pyramid. And so we learn here, for example, here in this example, cars, at that particular scale, and then we have as negatives both cars at different scales as well as non-cars. The nice thing about this is we can see here that we actually do get this logarithmic scale. This is the right scale. These are the ones we train as negatives. We actually get, on top of a better classification, we actually do get a real depth signal here. So that's quite nice, and of course we could use that and plug that straight in the previous work I showed. So now I'll just flash over this. We can extend our approach from the 3D semantic reconstruction. We can actually bring in here a regularizer. We can make it location dependent. Okay, by making location dependent, we can actually learn implicit shape priors. Okay, so we can learn the statistics that at the top of the car, the normal is pointing a certain way. At the bottom of the car, it's pointing the other way. In the front, the windshield is at 45 degrees. All of these things we can learn, and we can put this in a volume. It's actually very easy to translate the probabilities of the normals in a convex approximation as these wolf shapes, to construct wolf shapes that are a good approximation to the normal distribution. And then we can essentially learn these shape models. You see here some examples. Actually, I may switch to this here. The nice thing is that at the same time, it will actually then segment. So we get better reconstructions, but also we segment them. And for example, we can learn, here again, a normal reconstruction would collapse the car and the ground. Here we learn that the car, and this is the non-metric part, we learn that the car doesn't directly transition to ground. It transitions first to free space and then to ground, and that's cheaper to do the double transition than do the single transition. Except, of course, at the 4 contact points, wherever we learned in the data that the car was on the ground, there we learned that it's likely to transition to ground directly. Okay, this also means that if we learn the car here, we can learn that a car, we haven't done this here, but it's trivial, to essentially the car is likely to stand on a surface that's labeled road and less likely to be in your garden or something like that. Okay? This is just flows in this framework here. Here's a quick example on applying this to faces. Lots of missing data. We don't have the back here. We also do semantic labeling. This is the standard parametric model, so the state-of-the-art Vetter and Blanz type of models that you adjust to your data. This is our type of models. So we can have the prior, the shape prior, or implicit shape prior, applied to only the face area here, the skin area, which actually satisfies, but the hair and other things can be very different. Also, compared to a parametric model, if there's something, this was a raisin in this case, that we put on his face like a big mole to emulate a big mole, this can actually, in this it cannot be captured with a global model. But in our case, we have a regularizer that prefers to regularize according to the most likely shape, but if there's local evidence to the contrary, it will just follow the data, okay? Because it's just a regularizer. And also, actually, this was just showing that we can easily throw in a transformation there and optimize also our cost to have the best alignment in the data, which allows us to not need a perfect alignment from the start, but just have that optimized over. Another idea is that we can only do, generically, with these wolf shapes, convex shapes. Or we can do, of course, these implicit shape priors, but then we need to somehow align approximately at least a bounding box to get started. However, if you're willing to pay the price to go to model more classes, more subclasses, essentially, you can say, well, a table which is highly non-convex consists of actually two subclasses, which is the table top and the table legs, which each of them is convex. But not only can we define the likelihood of the shape of these shapes, but we can actually say that a table leg is something that in general is like infinitely extended, except if it finishes at a table top on the top, and at the bottom it finishes on the ground. So we can model all of this explicitly in this kind of grammar to describe these shapes. And so of course this works much better, I'll skip that, than if you just do from the data. It can complete data much better, essentially. Again, missing tree trunks here can be made to connect. This is from aerial images where you don't see the trunk. And then here, last one that I wanted to show is here a mug, which is interesting because, of course, a mug is highly non-convex. Don't look at the handle, but just the inside here. It's, of course, maximally non-convex in a sense. You can never slice it up in a number of convex pieces. However, if you actually look at the inside of the cup, the free space inside the cup as a convex object, and then the cup containing the inside as another convex object, it's actually both two cylinders, and it's very simple. And here again, we need the non-metricness, because what we can say is the inside of the cup can never transition, at least on the sides, and the bottom should never transition directly to free space. So the inside free space should not transition directly to outside free space, but it should actually always first go to outside, to the mug itself, the mug surface, and then only to free space. So again, we need a non-metric property here. Okay, and so I'll skip this here. We can actually easily throw in many other properties here, but I'll leave it at that. So essentially, we have the key message here was that by doing these two problems, or actually trying to solve all of vision at once, we can do this with this volumetric multi-class formulation, at least in this type of vision problems. The key thing is that we can get a strong coupling between the two subproblems, the geometry and the appearance, by having this link through this anisotropic behavior. If we know what it is, if we know it's a wall, we have a prior that essentially it's probably vertical, and we can fill in very nicely vertical surfaces if we miss data. Vice versa, if we have geometry, if we don't know, if our classifier doesn't know what it is, it's maybe ground, maybe a wall, but if it's vertical, well, okay, then it's a wall, right? So essentially, by solving both together, both can help each other. So the nice thing is the clean energy formulation, tight convex relaxation, at least up to the pixel ray modeling. Qualitatively, it gives a real improvement in terms of the geometry and also in terms of the classification, actually, because we get a full joint over all images, consistent classification. And of course, those semantic models are much more useful. In Switzerland, you have a number of, you have a limit on how much volume of building you can put on a parcel. Okay? Here, you directly get that. If you just get a surface, it's very hard to differentiate between vegetation, building, and other things. Okay? So you can answer more questions with these type of models. Okay? Now, there's of course many challenges, and I don't have time to discuss those. Many challenges to extend this, but also a lot of potential. And essentially, I want to thank you for your attention, and I'll take some questions at a time.